All right, welcome to the Explainer. If you are deep in ARE study mode, you've definitely come across a topic that can feel, well, a little abstract, the structural diaphragm. But today we are going to crack that code. Seriously, we're going to boil it down to one super simple idea that's going to make everything click into place. Let's do it.
Okay, so here's our game plan. First, we're going to talk about the basic problem, why we even need these things. Then, we'll get to the one core concept you have to remember. After that, we'll break down the parts, trace how forces actually move through the system, and, of course, wrap up with how this all shows up on your PPD and PDD exams.
All right, first up, the sideways problem. Let's dig into the fundamental challenge that every single building, no matter how big or small, has to solve.
I mean, think about it, right? We spend so much time designing for gravity, the force that pulls everything straight down. But what happens when the push comes from the side? When you get a huge gust of wind slamming against a wall, or the ground itself starts shaking in an earthquake? How do these massive flat floors and roofs take all that sideways energy and get it safely down into the ground? That right there, that's the whole reason structural diaphragms exist.
And that brings us to the brilliant solution. Seriously, if you only remember one thing from our time here today, make it this idea. I promise it will completely change the way you look at buildings.
So what's the textbook definition? A structural diaphragm is basically a horizontal system. Think your floor or your roof that acts like a big flat plate. Its whole job is to catch all those lateral forces, spread them out, and then hand them off to the parts of the building that can actually handle them, like shear walls or braced frames. But here's the real magic. Forget that technical definition for just a second, and picture this instead. A diaphragm is just a giant beam that's been flipped over on its side. That is it. That's the secret. If you can picture a huge, deep beam lying flat, you already understand 90% of how a diaphragm works.
Okay, so if it's a giant horizontal beam, then what are its parts? Let's jump into section 3 and build this thing out, piece by piece.
And this is where it all comes together so beautifully. It's a perfect one-to-one comparison. The sheathing, that big flat plane of plywood or metal deck or concrete, that's the web of your beam. It's what resists all the shear. Then you have the chords, which are basically the edges of the diaphragm. They act just like the flanges on an I-beam, taking all the tension and compression from bending. And then you have these special pieces called collectors or drag struts. Just think of them as force highways, grabbing all that load from the web and dragging it over to the walls.
Now, beyond those main pieces, the RE is absolutely going to grill you on the details. You've got to know about boundary nailing. That's where you have a much tighter pattern of nails or screws right at the edges where the stress is the highest. You also have to understand the physical connections, things like metal straps and anchors that actually do the work of transferring the load. And for wood systems, you need to know about blocking, which supports the edges of your plywood panels.
Okay, section 4. How do the loads actually get moved? We know the parts now, so let's put it all in motion and trace exactly how this system keeps a building standing.
This slide is everything. This is the load path, and you really need to be able to trace this in your sleep for the exam. Here's how it goes. A force hits the surface. The sheathing, our beam's web, carries that force across the diaphragm in shear. The collectors then kick in, grabbing that force and pulling it towards the walls. The load gets transferred into the shear walls or frames. And finally, that vertical system carries the load all the way down to the foundation. See, it's a simple, continuous story.
Now, not all diaphragms are created equal. A flexible diaphragm, like you'd find in the typical wood frame building, acts kind of like a flimsy piece of paper. It bends, and because it bends, it distributes the load really simply, based on tributary area. Basically, each wall just takes the load from the half of the diaphragm closest to it. But a rigid diaphragm, like a big concrete slab, is totally different. It acts like a stiff plate of steel. It does not bend. So it distributes forces based on the relative stiffness of the walls. The strongest, beefiest walls take the biggest share of the load, no matter where they're located.
And that brings us to section 5, probably the reason you're here, passing the ARE. Let's really focus on how PPD and PDD are going to test you on this stuff.
Okay, for PDD, you need to be thinking conceptually. The big picture. They'll ask you to identify a load path, choose the right system, flexible or rigid, or place shear walls in a logical layout. But for PDD, it is all about the nitty-gritty details. Can you actually specify a nailing schedule? Can you draw the connection between a collector and a shear wall? Can you size the chords? PDD is the what and PDD is the how.
You have to be on high alert for these common geometric curveballs the exams love to throw. Big openings for stairs or atriums, those need special framing. Buildings shaped like an L, T, or U, those create major stress hotspots at the inside corners.
Walls that don't line up from one floor to the next, you'll need something called a transfer diaphragm to bridge that gap. And an expansion joint? That's a total break. You have to treat it like two separate buildings, each with its own complete system.
And on the PD side of things, pay super close attention to the details of how everything connects. The exam loves testing chord continuity. Remember, those chords are taking tension and compression, so they have to be continuous. And any splice has to be just as strong as the chord itself. The connection of the collector to the shear wall, that is a classic weak point. And anchoring a diaphragm to a masonry wall is a favorite topic. Oh, and don't forget that big, heavy equipment on the roof adds a ton of mass that the diaphragm has to deal with in an earthquake.
So here's your mental checklist. Whenever you're looking at a practice problem, run through these questions. Can I trace the load path? Are the chords continuous? Are collectors where they need to be? How are openings and corners being handled? Is that an expansion joint? Are the boundary details specified? If you can confidently answer all of these, you are in fantastic shape.
Look, if this all feels like a lot to remember, just bring it back to this one single idea. Always trace the load path. For any question on any drawing they give you, your very first instinct should be to put your finger down and trace the path of a force from the surface, across the sheathing, into a collector, down a wall, and into the foundation. If you can do that, you've got this. And that's our deep dive into structural diaphragms. So, the next time you walk into a building, I want you to look up at the ceiling or down at the floor and try to see it, that hidden, giant, horizontal beam that's holding the whole thing together. Thanks for tuning in.